Wow, wasn't that cool stuff we learned so far about electromagnetic energy? So let us finish this off and let's just see if we can clean this up a little bit before we start our first consider. So we have electromagnetic radiation, right? And we said, hey, what is electromagnetic radiation? We said it's a form of energy. And what do we talked about some characteristics. We said it has a wave particle duality, right? And what did we mean by that? We meant that, hey, it travels like a wave. And what do we mean by it travels like a wave? It has a wavelength and it has a frequency, right? And the wavelength is the distance between corresponding points on adjacent waves, and frequency is the number of waves that pass a certain point per time. And then we also said that it has properties like a particle. It interacts with matter like a particle, like a particle, like a particle. And what did we mean by that? We said, hey, it it shoots out a stream of photons, and photons are kind of a chunk of energy, a massless particle carrying a photon, carrying a quantum of energy, right? So there we go. And then we said, hey, we have this thing called the electromagnetic spectrum, and that's an ordering. We have the spectrum and the spectrum, and that kind of orders my electromagnetic radiation by increasing wavelength or decreasing frequency or, oops, I did this wrong. Yeah, that's right. Decreasing energy, right? That from left to right, my wavelength increases. From left to right, my frequency decreases and energy decreases. And so we said over here that, hey, gamma rays are small wavelength, but that means big frequency and big energy, right? And over here I have radio waves, and they are big wavelength, and that means small frequency and small energy. And now how do we know, oops, small energy. And how did we know that? Because we had some um, equations, right? We said that c, the speed of light, equals my wavelength times my frequency. And then we said E, the energy of my photon, the energy of this guy right here is equal to H, Planck's constant, and we don't really care what that is, nu, or it is equal to Hc over lambda. So as my wavelength goes up, what happens to energy? It goes up. As my, frequency goes up, my energy goes up. As my wavelength goes up, it's in the denominator, so my energy goes down. And so that's kind of the overview of where we are so far. So let us move on one step farther. Consider the atomic emission spectrum of hydrogen. Oh man, what is that? Oh, when we have this thing here, okay, first of all, here's sodium, so we don't care about sodium. Here's H, hydrogen. Well, what is an atomic emission spectrum? Well, it is a set of characteristic, what does that word mean? Characteristic. That means it is unique to that atom. Set of characteristic electromagnetic radiation. Electromagnetic radiation emitted by an atom. I guess I should say what atom or element. What do you think is the best way? By an atom of each element. How's that? By an atom of each element. And we have the important word here, I think, too, characteristic 3, electromagnetic radiation. What that means is it is unique. It is unique to every element. So when I say that this is the atomic emission spectrum, and we'll call it an AES, of hydrogen, that means it is unique to hydrogen. It is like hydrogen's fingerprint, electromagnetic fingerprint, electromagnetic fingerprint. If I see this kind of pattern, I can conclude that hydrogen is making that. Good. Now, here's the question. Why is there always a line at this 35 nanometer? Okay, where are we? Where's my 35 nanometer? Right here. And we really didn't have to just say this one. We could have said, hey, why is there always this line here, and why is there always this line here? Because it is characteristic. That means every hydrogen atom will, when it's excited, will produce this line spectrum. So why is it always there? Okay, here's what we have to understand. We're really going to get ahead of ourselves a little bit and talk about Bohr for a second. Now, think about it. Let's talk about how do you just get this electronic spectrum stuff. Well, we would have a source of energy, so this is plugged into the wall, and in there we'll put a tube, and that tube has some hydrogen in it. And then we get it excited, and then we'll see a color, right? And I'm not sure it's that color. It's more like a purplish color. Okay, but I don't have purple handy. And then what we do is we take something called a spectroscope. And the spectroscope is essentially a prism, and it will break the total color down into a line spectrum. And then here's your eye. And you're looking into this. And in fact, you're going to do this. Now let's give you a nose. You're going to do this in the lab soon. And so you look at this, and then when you look at this, what do you see for hydrogen? You see this spectrum. And the question then is, why do you see this stuff? Well, what happens? What produces the light? What produces, because this is light, right? These things here are different colored light. And the question is, what produces that? It has to come from somewhere. Does it come from the electricity? Not really. Here's what happens. Here's my proton, right? And I have an electron. Let's say this is hydrogen, so I have one electron. So here's the electron. I put energy into it, and what happens to that electron? Well, it gets what we say is excited. So it will jump. It'll go farther away from my nucleus. Here's my nuke. So that electron jumps. And in fact, we say it jumps a level. That we have an n equals 1 level, an n equals 2 level, n equals 3 level, right? And it jumps a level. Now, when it drops back, it wants to come back to the ground state. When it drops back, what happens? Well, for it to jump, we said it had to get energy. So when it drops back, that means it shoots out a photon of energy. Good. So the easiest answer so far is, what causes these lines? Well, the cause of these lines is photons, or are photons emitted when excited electrons drop to lower energy levels. Okay, that's why we get colors. Now the question is, why are they always the same? Well, think about this. Let's think logically here. If these colors are always the same, what must that mean? And remember, colors, we have to go back. What are colors all about? Hey, if I have a certain color light, that means it has a certain, well, let's see, 430. Right here is about 430. If I have a certain color of light, it has a certain what? Wavelength. If it has a certain wavelength, then it also has a certain energy. So the different colors of light indicate what? Different colors of energy. So this means that this represents one energy, and in fact, it is a lower wavelength. So that means this is a higher energy. And then this has an energy which is somewhat less than this energy. And then this one has an energy, and it is less than this energy. So the question is, why would I get three different energies being produced, three different lights um, of different energy being produced from an electron getting excited? Because there's only one electron in hydrogen. So what can that mean? Well, here's what it means. I have an electron, right? Well, that electron, we'll say it's in n equals 1. It could jump, well, let's say n equals 2. It's at n equals 2. Here's n equals 1. We'll say it's already, though, at n equals 2. Well, it can jump, right? Well, it can jump to n equals 3. It can jump to n equals 4. It can jump to n equals 5, right? If it jumps from n equals 2 to n equals 3, it's going to do what? It's going to fall back. Let's say it falls back to n equals 2. Now it emits a photon. Now, is that a big jump or a small jump? Well, from 2 to 3, that's kind of a smaller jump. So if it's a smaller jump, then we'd expect it to be smaller energy emitted. What if it goes from 2 to 4, and then what happens? It returns from 4 to 2, and oops, yeah, that's right. It returns 4 to 2, and then what happens when it returns? When it drops down, it emits energy. Now that energy is of green light, and so it is higher in energy. Why is that? Because there's a bigger drop. And then finally, let's assume this electron that started at n equals 2. It could have started anywhere, but we'll say this one just started at n equals 2. It jumps all the way to level 5, and when it drops back from level 5 to n equals 2, what's going to happen? It's going to emit a photon, and that photon is going to have an energy, and that turns out to be a blue line. So the color of the lines is indicative of the size of the jump. And what do we mean jump? Well, Bohr is the guy who came up with this whole thing. He looked at that electromagnetic spectrum and said, hey, we have things called orbits, and that electrons can only exist in these orbits, that they cannot exist in between the orbits. And so an electron has to be in a certain orbit. To go from one orbit, we'll say from n equals 2, to go from n equals 2 to n equals 5, it must absorb energy, quanta of energy, or a quantum of energy. And then when it drops back, what must happen? It must emit quantum of energy in the form of a photon. Holy moly! Is that what the answer is? Yes, that's the answer. Why is there always a line at 430? Because that represents the drop of the electron, the consistent drop of the electron from the 5th energy level to the 2nd energy level in hydrogen. It is always the same drop. Why is that? Because the electrons are always in the same places. Okay? Good. We're almost done. Ooh, mama. Consider the hydrogen atom. Is an electron in the 3rd energy level in the ground state? The answer to that is no. Now, how do we know that? Well, the ground state, we just have to define it. What is the ground state? It is the energy level. This is the energy level closest to my nucleus. So this is the energy level available. This is, how do I want to say this? This is the, I'm going to say it a different way. This is the electron state of lowest energy. I like that better. And by lowest energy, that means closest to the nucleus. Now, sometimes if I have multiple electrons, then I may not always be in n equals 1. I might be in n equals 2 or n equals 3. So my ground state is the electron state of the lowest energy for the electron. Good. And then an excited state would be what? An excited state would be any state for the electron. Any energy state is what we're talking about. Any energy state for the electron that is greater than the ground state. And so that also means farther away from the nucleus than the ground state. So is the electron in the third energy level in the ground state? The answer is no, because the ground state would be where n equals 1, meaning the first energy level. Okay? Finally, last two, and then we're done. Here we go. Consider an electron dropping from n equals 8 to n equals 3 in a hydrogen atom. What is the wavelength of the photon, and is this visible light? Okay, so let's figure out how to do some calculations. There's a guy named Rydberg, and he came up with the Rydberg equation. And what he said this is 1 over lambda equals 1 over 91 nanometers. Now we only have 2 sig figs here. Times 1 over n sub L squared minus 1 over n sub H squared. Okay, what does that mean? Okay, so I have my nucleus, and I have my orbits, and I have n equals 1, n equals 2, n equals 3, n equals 4, and so forth, okay? Where each n represents an orbit state. Now, by the way, this is slightly wrong. You'll learn next lesson that orbits don't really exist. There are other things called orbitals, but this is what Bohr was doing in 1911, 1913, okay? So these are my energy states of the electron. And NL means my lower energy state. NH means my higher energy state. So let's go to the question again. What was the question? We are going to drop from n equals 8, my 8th energy level, to n equals 3. Okay, 8 to 3. So that means I'm going to take n equals 8. We'll put n equals 8. And n equals 3. I'm going to go from n equals 8 to n equals 3. N equals 8 is my high energy level. N equals 3 is my low energy level. So let's solve this. 1 over lambda is equal to 1 over 91 nanometers times what? 1 over NL. NL is 3. 1 over 3 squared minus NH is 8. 1 over 8 squared. Good. Now, we have to be careful with the calculator here, folks. This is in the denominator, so let's work this carefully. 1 over lambda is equal to 1 over 91 nanometers times 1 over 9 minus 1 over 64. By the way, these are defined, so there are infinite sig figs there. This is what's driving our sig figs, the 91. And so what do we get out of this? 1 over lambda is equal to, I take 1 divided by 9 minus 1 divided by 64. And I get 1 over 91 nanometers times 0.09548. Good. Let's keep going. 1 over lambda equals, take that number and divide it by 91, and I get 0.001049, 1 over nanometers. And now what do I have to do? I have to take the inverse of this. So what is the inverse key? If you hit 1 over x on your calculator, that button, that's your inverse key. And what do I get then? When I hit that, I get lambda is equal to 953. I can only have 2 sigs, so 950 nanometers. So the photon that is shot out when an electron drops from the 8th level to the 3rd level has a wavelength of 950. And what was the question? What is the wavelength? We said it's 950 nanometers. Is this visible? Let's go back to our spectrum and find out, is this visible? Oh my gosh, let's erase some stuff so we can see. 950, where is 950? Well, here's 750. 950 is somewhere over here. It means it is beyond the visible spectrum. It's probably in my infrared range. Good. All right, here you go. Let's see if you can do this on your own. Pause me, and when you're ready to answer it, defrost me. Well, I hope you got an answer. Here we go. 1 over lambda is equal to 1 over 91 nanometers times, okay, this is my NH. This is my NL. 1 over NL. 1 over NL. Oh, 1 over NL squared minus 1 over NH squared. So that means this is equal to 1 over 91 nanometers times 1 over 4 minus 1 over 36. So this is equal to 1 over 91 times 0.25 minus, I don't know 1 over 36 on the top of my head, minus 1 divided by 36. That would be 0.0277, blah, 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 blah. So what do we get here? 1 minus 1 divided by 36. Okay. And divide that by 91. And so what I get is 1 over lambda. Be careful here. 1 over lambda is equal to 0.00244. Now what do I want to do? I want to take the inverse of that because that flips both of these. When I take the inverse, I get lambda equal to 409.5. How many sig figs? 2 sig figs. So lambda is equal to 410 nanometers. And notice this is in nanometers. 410. Let's go look at our 410. Where's 410? Hey, 410's here. Looks like that is what? Violet. So is this visible? Yes, it is violet. Okay, that would be it for electromagnetic radiation. See you next time when we get into the history of the quantum atom. Thank you and bye-bye.